Hello everybody and welcome to Circuit Analysis 1. We're discussing Chapter 13. These are the sections you should read, 1 through 8. Here's the video lessons, 23 through 27, and here's the URL to get to that. We're going to talk about AC sinusoidal waveforms. So we're moving from direct current, DC, to AC, alternating current, and we're going to concentrate on sinusoidal AC signals. We're going to learn the meaning of these types of characteristics of an AC sinusoidal waveform. And the reason we are going towards AC, more or less, sinusoidal, is because these are the type of signals generated by utilities worldwide, and it's in use in electrical and electronic circuits. So the peak value of this waveform is 8 volts. The instantaneous value at 0.3 would be -8, and at 0.6 would be 0. What's the peak value? The peak-to-peak value. So the peak and the peak here. So we have 16 volts peak to peak. What's the period of the waveform? That's where it starts over again. But there's a number of ways to determine that. You can look at the peaks and subtract from where they are. Or you can look at the origin and go in, this one's perfect, it starts at the origin, but they're not always that clean. But 0.4 seconds is the period of this waveform. It's when it starts over again. How many cycles are shown? Well, we have 1, 2, 3 and a half of 1. So 3.5. What's the frequency of the waveform? You take the inverse of the period to get the frequency. So the period was 0.4 seconds. The inverse of that is 2.5 cycles per second, and we call cycles per second hertz, so it'd be 2.5 hertz. Because of the wide range of various frequency bands in use today, the government has regulations to control the use of the frequency spectrum to avoid interference from one another. Now we could plot a sine wave with the y-axis as the magnitude and the x-axis in either degrees or radians. So, and this is the mathematical expression that we use. We have the peak amplitude here, a sine, omega t, which is the angular velocity times time, plus or minus some phase shift. These wouldn't have a phase shift because they're starting at the origin. However, if we moved it to the left, it'd be a positive phase shift. If we moved it to the right, it'd be a negative phase shift. So here's how we would, given a frequency to determine the period. Some examples there. And given a period and find the frequency. We can plot a sinusoidal waveform in time or by the angle. The time in seconds or the angle by degrees or radians. This graphic demonstrates how to move between the degrees and radians. So a lot of times we use pi and 180 degrees for converting between them. And this will give you the definition of how they determine a radian. So you can read that in your spare time. So we must be able to convert between radians and degrees with this type of work. And the period is one complete 360 degrees or 2 pi cycle when the waveform starts over again. The angular velocity is the rate at which the radius vector rotates around the center as shown by the circle. So this radius vector is inside the circle, and then how fast it moves is the angular velocity. So the angular velocity is in radians. And if you're given a frequency to determine the angular velocity, we can use 2 pi over the period or 2 pi f, the frequency, to determine that. So there's a couple examples there. Now here is the expression of a sinusoid, And here's a problem where we're given this expression of 20 is the amplitude, sine 2000t, the angular velocity is 2000. What's the amplitude? It is 20. And what's the angular velocity? It is 2000. What's the frequency? We can do the angular velocity equals 2 pi f, and we can determine the frequency. Then we can determine the inverse of the frequency to determine the period. What would happen if the value of this, we want to find out what is the value at 2 milliseconds. Well, we'd plug 2 milliseconds into t, multiply it times 2000, get the sine of that, times 20, and we get 1.4 volts. Leading and lagging indicate the relationship between two sinusoidal waveforms of the same frequency plotted on the same set of axes. Now, if the waveform shown is a voltage with the phase shift angle of 45, so if that theta there is 45, and we had an amplitude, say A sub m, the amplitude is 10, the expression here would be 10 sine omega t plus 45. So remember, if it's shifted to the left of the origin, it's positive. So I kind of put these definitions here. Shift to the left of the origin is positive phase shift. Shift to the right is a negative phase shift. If we're given these two waveforms, which one is leading? So the leading waveform is the one with the 0. If there's no angle given, it's considered to be 0 degrees. And it's leading by 50 degrees. V1 leads V2 by 50 degrees. Now, just go over these. In DC, power is volts times current, volts squared over resistance, or I squared R. When we compute power for an IC sine wave, for a sine wave, it gets a little more complicated. It's actually the average power. And we use RMS here, voltage RMS times the current RMS times the cosine of the angle. Now, if it's a purely resistive circuit with a resistive load, it would be a cosine of 0, which gives you a value of 1, so it'd be transparent here. So we notice that the voltage RMS is equal to the peak divided by the square root of 2. So if we're given peak values, we can put it here of the square root of 2, and square root of 2 times square root of 2 equals 2. So this will be our formula for given the peak values, and here's our formula for the RMS values. And here's a little information about measuring RMS on a volt-ohm meter. You have to have a really good volt-ohm meter to give you a true RMS value. So if we're given these two sine waves, one's a voltage and one's a current, which waveform leads in by how much? So the voltage leads by 10 degrees. Here, the current leads by a delta of 70 degrees. Write the expression for 60 Hertz power supplied to a receptacle in a home. So this is the kind of expression we want to get to. So the volts RMS is assumed to be 120 volts. And so here's our value for RMS. So if we want to find the peak value, we rearrange this formula to square root of 2 times the volts RMS. So I'll do that. Square root of 2 times the volts RMS equals 170 volts peak. And so what is the angular velocity? We know it's a 60 Hertz waveform. That's what the frequency is of our utility given to us at our home. So 2 pi 60 is 370. So this is the expression for voltage at your receptacle in a home. 170 sine 370 t. And we're just assuming it's starting at the origin. So for homework at chapter 13, do these problems. Have a great day.